Firstly, I should apologize that I couldn't get a satisfying answer to the question that people were asking last week for what is an example of two distinct, indiscernible, non-standard numbers, or why should distinct, indiscernible, non-standard numbers exist. I did find some proofs in the literature, but that would also require the assumption of some other facts about non-standard numbers, some set theory business. So maybe we can discuss that at the end if people are still curious, but I don't want to open up with it since, in my opinion, the answers that I have are not as satisfying as they could have been. So that being said, I'm just going to continue with the original plan for the last part of the talk, which is just to tell you guys the statement of the minimal Rado condition and show some examples of polynomials which do not satisfy it and are therefore not partition regular, and maybe have some more remarks and discussion about how this is all related to the original Rado theorem for systems of linear equations and so on. So let's get right into it. We just need a couple new definitions that we didn't have from last time. So if we have a polynomial equation, p of x1 to xn equals 0, then I will say that it is Q partition regular if for every integer k and every partition of the multiples of q to the k, there is some set in the partition and some elements in that set which satisfy the equation p of x1 to xn equals 0. Now, I would like to believe that if a polynomial is homogeneous and this equation is partition regular, then it should also be Q partition regular. But I have not found the proof of that. This is not stated in the paper on which these talks are based on. So I suppose that's still open. It's a amusing fact, or just a amusing question to think about. Now, the only other definition we need, which is a little more complicated, is lower Rado functional. And this is pretty similar to upper Rado functional. It's, in fact, I'm 99% sure that they're almost interchangeable. I'll say a few more words on that in a moment. But lower Rado functional of order m, where m is allowed to be 0, for some polynomial is just a tuple, as we had before. So J0 to JL are going to form a Rado partition of the support of our polynomial. And then D1 to DM are integers for some m that is smaller than or equal to the number of elements of your partition. And D1 to DM are positive integers such that for any finite coloring of the natural numbers and every integer r, there are infinitely many C monochromatic positive linear maps such that the partition that you're given is the partition of the support determined by these maps. And if M0 to ML is the increasing enumeration of the values of the support when you evaluate it under this map, then the differences of the first m, or really mi minus m0, where I is from 1 to m, is going to be equal to these values that you prescribed. And then for all other values, we have mi minus mm is bigger than or equal to r. And really the only difference between this definition and the definition of upper Rado functional is that here the we're taking differences with the smallest element, the smallest value in the image of the support under our map. And for upper Rado functional, we were just doing the largest. So for upper Rado functionals, we wanted these values, the biggest ones, to be equal to the prescribed integers, and then these other ones, the smaller values, to be large. For lower Rado functional, we just switched the order. And the reason why I said they're almost the same, the only reason I'm hesitating is I haven't written down a proof that they're the same, but we saw last time, just to give you some idea, that you can do something of this form. Here. Right, we know that, or not last time, maybe 2 weeks ago, we saw that structures of the form a plus b minus 1 are partition regular. So then you can use this to create a functional. And if all you did was make if you shift in the other direction, then you can subtract things in the opposite order to get the same integer, which in this case is 1. The subtractions would give you 1. So then you just reverse which elements are the biggest and the smallest and the order in which you're subtracting things. So this is just intuitively how you could go from upper Rado functional to a lower Rado functional, and why they're almost the same idea. But of course, just due to the technicalities of the proof, for the minimal Rado condition, you would need a lower functional. Now, that being said, I guess this example here is pretty similar to what we saw 2 weeks ago, or at least the way in which I'm going to examine its functionals. So here I have a polynomial of 4 variables. It is w to the 4th minus 3x cubed plus 3y squared minus z. And for use on a future slide, we're just going to observe that if I define this new polynomial in which I set all 4 variables to be the same, then I can factor it as w times w minus 1 cubed. In particular, this p1 tilde factors as a product of, excuse me, it factors as a product of linear polynomials. This is not relevant for the definition of lower Rado functional, but it'll be relevant when we get to the actual statement of the minimal Rado condition. Now, the claim is that P has no lower Rado functionals of order m bigger than or equal to 1. And I won't go through all of the details of this, since I did this in a fair bit of detail 2 weeks ago for upper Rado functionals, and the idea is pretty similar. But I'll just give some outline, and if people ask me to, I can go into more detail. But if we have this map, So the general idea on how you would show this is if there was a lower Rado functional, then you could evaluate your functional at one element of the support and subtract from that the value of the functional at some other element of the support, and you will obtain the value d1, just one of the prescribed values, since your order is assumed to be at least one. And if we write out any of these subtractions, clearly there are more possibilities to consider than what I've written here. I'm only showing you some of the possibilities, but we can see that the possibilities will look something like this. For example, we can look at the 4a1 minus 3a2 equals d1. And this should happen for infinitely many different functionals phi, which are going to be monochromatic with respect to some given coloring. So that means that whatever your coloring is, there's infinitely many monochromatic, infinitely many distinct quadruples, infinitely many distinct monochromatic quadruples, A1, A2, A3, A4, that let you make this functional, such that 4A1 minus 3A2 is equal to D1.
Still it's funny to go put the points in the graph and just connect them with a line. Sorry guys. Sorry, it was I was speaking to a friend. Sorry.
Oh, okay. So now, if we consider any of these equations, we can use the nonlinear Rado theorem to start with. So this nonlinear equation is partition regular if and only if there exists a constant solution which would mean, if they were the same, then you would end up seeing that the constant is d. And then we see that in this case, if it was partition regular, you could rewrite it into this equation, or you could actually always rewrite it into this equation. But we now see that this equation is not partition regular because it does not satisfy the traditional Rado theorem. So you only end up getting the one solution. So this equation is not going to be solvable for infinitely many distinct tuples A1 to A4. And therefore, this cannot be the way in which we obtain the value D1 for our functional. And now you just repeat this for every possible pair of elements in the support of this polynomial. And you could see that because I chose these exponents in such a way that by the time you get to this point, the traditional Rado theorem is going to assert that there are no solutions. You will not obtain a lower Rado functional of order 1. So hopefully this was a refresher, because this is very similar to what I did 2 weeks ago. But I would still like to ask if there's any questions, because I guess this is a fairly important fact for showing that this polynomial is not partition regular. Okay. So now we can go ahead and state the minimal Rado condition. So we have a polynomial in n variables, and unlike the maximal Rado condition, we unfortunately are unable to work with any polynomial. We need an additional assumption. We have to assume that this polynomial, p tilde, which is defined by setting all of the variables to be the same, splits as a product of linear factors over z. And this is a, I suppose, fairly strong assumption, but having read their proof, I don't see of any way to remove it, which is unfortunate. So for now, we have no choice but to keep this extra assumption. And that's why I pointed out with the previous example, it does factor as a product of linear factors when you set all the variables to be the same. But if we go ahead and make this extra assumption, then the polynomial will satisfy the minimal Rado condition if for every prime p, there exists a root a of this polynomial and a minimal Rado functional, j0 to jl, comma d1 to dm, for the polynomial p, such that we extend the Rado functional by letting d0 equal 0, same extension that we had in the maximal Rado condition. And then this polynomial, which we'll look at in detail in a moment, should have an invertible solution in the p-adic integers zp. So, and of course, before we process this, the purpose of this definition is to get this theorem. If a polynomial is partition regular and this p tilde splits over z as a product of linear factors, then p satisfies the minimal Rado condition.
Sohail, can I ask something? So you don't have polynomials of the form n times n plus 1 over 2, for example?
Say that again? P of
n
equals
n times n plus 1 over 2.
Well, that does not, you're correct, we don't have these polynomials, but if we are looking at the equation then you can multiply it by 2 and this should not appear.
Okay.
So I don't believe that this causes any issues if you just make the adjustment here. Now, let's take a look at this polynomial. So this part should be familiar. This is similar to what we had in the maximal Rado condition. The sum I equals 0 to m of p to the di. These di's coming from the functional. And this w to the size of alpha should also be similar. The change is here. Now, you should all notice that if a is 0, then this is just going to be C alpha. And then you obtain a polynomial that looks the same as what we got in the maximal Rado condition. The only difference is that our roots are now in ZP instead of the real numbers. And hopefully it's clear to everyone what this means, right? Do I need to explain this definition in more detail? Because I'd be happy to, but I was just assuming that we all know. Okay, there's no question, so I won't go into that more. So if A is 0, we recover C alpha, and this looks even more similar to the maximal Rado condition, other than the switch over here. If A is not 0, this is just obtaining the coefficients of the shifted polynomial. And yeah, sorry. So this polynomial, when you shift all the variables by a, it might increase the support of the polynomial. It probably will increase the support, but I'm not looking at the extra elements of the support when you do this. This coefficient is just from shifting the polynomial by one of its roots, and then only looking at the elements of the support of this polynomial that were also inside of the support of the unshifted polynomial, right? Because these ji's were determined by the polynomial before we did any shift. Now, and the reason for this goes back to the definition of Q partition regular, because you'll see I did not mention Q partition regularity anywhere here, even though I gave you the definition on the second slide. So again, I'm not gonna go into any serious proofs here, but just to give you some idea as to why this is all related. So if the polynomial is such that p tilde of w splits over z as a product of linear factors, then p and the original equation is partition regular, then for any prime p, there exists a root r of p tilde such that p x1 minus r xn minus r is p partition regular. So in order to obtain that minimal Rado condition, we needed to know more than the fact that the polynomial was just partition regular. In order to get this extension to the p-adics, they needed to know that the polynomial was p partition regular. But as I mentioned earlier, it's surprisingly not an obvious fact that even just a homogeneous polynomial that is partition regular would be p partition regular. Intuitively, I thought that would be obvious, but it's not. So in order to guarantee this p partition regularity, this strengthening of partition regularity, they were forced to assume that the polynomial splits this p tilde over z, and then they could shift the original polynomial by one of the roots, and the shifted polynomial would end up being p partition regular. So that's why we have these extra technical assumptions here, and why this is a little bit uglier than what we had in the maximal Rado condition, but it's still all related. Any questions so far about the statement or ideas of this minimal Rado condition before I look at a few more examples? Like apply this condition to some examples. Okay, and maybe I'll just point out one more thing before I go to the next slide. Just like we had with the maximal Rado condition, we observe that if our functional has order 0, then this sum will only have this one term in it. And this one term is most likely only going to have 0 as a solution. If the J0 consists of a singleton, then there will only be one term here, and W will have to be 0, and that is not going to be an invertible solution. So what we'll end up seeing for the previous example, or the first example that I mentioned to you guys, is that I already showed you the only functionals are order 0, so we only have one term in this sum. Because I conveniently chose the exponents, the only Rado partitions are going to consist of singletons, so then your only solution will end up being 0, which is not invertible, and therefore that equation will not be partition regular. Right. So I guess maybe I just said it, but I should write it here. So to see that this is not partition regular, the only detail that I skipped over in my explanation on the last slide is to show you that the only Rado partitions of this polynomial consist of singletons. Well, maybe I shouldn't use X, Y, and Z. Okay, so I'm not going to go through the technical definition of Rado functionals again, but basically we want to know when we could apply a functional to these elements of the support, these exponents, and obtain the same value. If you obtain the same value, then you lump both of those terms together. So in order to obtain the same value, when I compare any two of these monomials, well, there's only 4 monomials, so there's 6 ways to pick 2 of them. Either 4a1 equals 3a2 if I wanted the image of these 2 guys to be the same, or 4a1 equals 2a3 for this and this, 4a1 equals a4 for this, 3a2 equals 2a3 for this, and 2a3 equals a1 for this. None of these homogeneous equations satisfy the traditional Rado theorem, or the columns condition, if you would like. So therefore, there is a partition. For any one of these equations, there's a partition for which there is no monochromatic solution. If you take the common refinement of all 6 partitions, then there will not be a monochromatic solution to any of these equations. And therefore, the only Rado partitions of this polynomial will consist of distinct singletons. So then by what we said on the previous slide, if you only have Rado functionals of order 0, and all of your Rado partitions are distinct singletons, then you will not have an invertible solution in ZP, so your polynomial is not partition regular. And I'm not going to go through these in as much detail as I just did with example 1. So are there any questions about example 1, or would you like me to review or reiterate any part of it before I continue? Okay. So these next 2 examples, these are from the paper of Barrett, Moreira, and Lupini. So their first example is this polynomial P2 of xy, which is x squared plus y squared minus xy minus ax minus by plus ab, where a and b are some constants, but they're the parameters that we're varying. X and y are the variables of the polynomial. Now, the first thing to note is that if a is equal to b, then xy equals aa is going to be the only solution to this equation. So the polynomial equation will be trivially partition regular because you could always take this constant solution, but we don't really care about trivial partition regularity, so it's not a non-trivially partition regular. If a is not equal to b, then they show in their paper that this polynomial does not satisfy the minimal Rado condition. And they have some other general remarks about some basic conditions in which the minimal Rado condition is not satisfied, but I'm not going to state them here. I'll direct you to their paper if you're interested. The only thing that's maybe easily checkable and worth checking here is we just see that P2 of xx is equal to x squared minus ax minus bx plus ab, which is x minus a times x minus b, right? And it turns out that in this next example, we have the same thing as well. So I'm assuming that their reason for investigating this polynomial is, one, I don't believe partition regularity of this was known, but this is, I think, the simplest example of a polynomial which the p tilde, when you set the variables equal, will factor as a product of linear polynomials, right? The example I gave was a quartic example, but this is a quadratic example. Now, similarly, their next example, all they did is they changed the signs here. So the plus y squared became a negative y squared, the plus xy became, or excuse me, the negative xy became a positive xy. And this time we can just say that if a does not equal b, then P3 does not satisfy the minimal Rado condition. And I don't believe they had any remarks about what happens if a is equal to b. And then they concluded with this conjecture that if we have a polynomial such that p tilde is a non-zero homogeneous linear polynomial, then the equation p of x1 to xn equals 0 has infinitely many solutions in the natural numbers if and only if, excuse me, I was thinking the wrong thing. We also assume that the equation P of x1 to xn equals 0 has infinitely many solutions in the natural numbers. Then it is conjectured that the polynomial is partition regular if and only if it satisfies the maximal Rado condition and the minimal Rado condition. So to even try to check the minimal Rado condition, they would have to assume that P tilde splits as a product of linear factors. But we can see here, they're making an even stronger assumption. They're assuming that it's homogeneous and that it simply is a linear polynomial, not that it splits as a product of linear factors. They didn't give any further evidence to support this conjecture in their paper, because even the examples that they considered, the P tilde is not linear, it's quadratic. But this still seems like a nice strengthening of the assumptions, and I'd be happy to see if it's true or not. And that's all I had prepared for today. So we might just finish early, but are there any questions about anything from today or from the last 2 weeks? I guess I could go into some a little bit more discussion about how this ties into the original Rado theorem, but before I proceed to that, any questions? Okay. So So you could rephrase Rado's theorem in the following way. So if you take a matrix So this homogeneous linear system of equations is partition regular if and only if for any prime p and any, well, I already used n, integer L, ax equals 0 has a monochromatic solution in the partition n well, yeah. The partition of n in which x, y are in AI if and only if the first L non-zero digits, well, that's not quite correct. The first L digits of the base P expansion of x and y, P expansions of x and y, x and y, starting at the first non-zero digit, is the same. Okay. So in order to know if a system of linear equations is partition regular, you only have to check countably many partitions. If the system is partition regular over these countably many partitions, then it simply is partition regular. There will be a solution for any partition. And this is fairly surprising because we all know that partitions correspond to ultrafilters, and the number of ultrafilters, or the cardinality of ultrafilters on the integers, is the cardinality of the power set of R. So this is, I guess if you assume some version of the continuum hypothesis, this is 2 orders of infinity larger than countable to encompass all possible partitions. And we're saying that if you just are partition regular over these countably many partitions, you will be partition regular over these aleph 2 number of partitions. Forgive my set theory if that wasn't accurate. And the work of Barrett, Lupini, and Moreira supports or continues this ideology into the nonlinear realm. So the minimal Rado condition, which I just discussed today, is what you will obtain if you extend this idea, this partition, using non-standard analysis. If you try to apply the proof that I discussed with you guys last week, but starting with the first L digits in the base P expansion instead of the last L digits in the base P expansion, then you will enter the p-adics and recover this minimal Rado condition. And actually, I should warn you guys here. I use different terminology than what is used in the triple paper. Whenever I think about the first L digits of the base P expansion, I'm thinking about the smallest digits, the smallest non-zero digit. And I got confused the first time I was reading their triple paper, because when they say the first digit in the base P expansion, I believe they were referring to the biggest digit. So there is a little discrepancy to be careful about in case you do decide to go read their paper. But yeah, so the minimal Rado condition naturally extends this idea. And then the maximal Rado condition, while it is a natural twist on this idea, it takes the L digits on the opposite side, what I would call the last L digits and what they would call the first L digits. It's also worth noting that the maximal Rado condition required a solution to some polynomial, not in ZP, but the real numbers. And if you've ever taken the course in algebraic number theory, you know that the only possible completions of the integers with respect to a norm not a norm. I guess I'm sorry, I can't articulate this precisely, but with respect to one of the Archimedean norms, or one of their multiplicative I'll just say one of their number theoretic norms, the only possible completions are the real numbers and all of the p-adics. So there seems to be something. Thank you, Andrea. That's the word I was looking for. The only possible completions of the integers with respect to any valuation is either the p-adics or the real numbers. So there seems to be some strong connection between partition regularity of polynomial equations with number theory. Just the fact that these p-adics and real numbers are showing up, and the fact that this connection to the p-adics, right? This is certainly a, I would consider these partitions based on the digits of the base p expansion to be very p-adic in flavor. The fact that this happens to be necessary and sufficient for linear equations shows some sort of connection to number theory as well. I would personally like to have a good explanation as to why, in the linear case, we don't need to consider the real numbers. We don't need to consider the completion with respect to the standard Archimedean norm or Archimedean valuation. But yeah, as far as I know, I don't currently have a good answer to that. So I believe that's all I have to say on the topic. Just want to point out this connection to number theory, and I would like to believe that there's something more there, even though I don't know what it is and it's not stated in their triple paper. So with that, I think it's time for a little bit of Gauss. I did want this to be on the recording, so. Any questions before I stop the recording?
You spoiled my question. I was about to ask where is Gauss.
Yeah,
honestly.
And observe that I still ensured we had a prime number of slides. That was intentional. So yeah, I guess I'll go ahead and stop the recording here.